In this lesson, we're going to convert words or sentences to differential equations. What I want you to realize right off the bat is that a differential equation involves nothing more than a rate or a derivative and an equal sign. With that in mind, let's go ahead and learn how to convert some of these words. Some preliminary things to know have to do with proportions. The first two are the most important. First, we have directly proportional. With directly proportional, that means that both y and x are related based on a constant k. So if you take a constant k and you multiply by x, you get y. For example, let's say k is 2 and x is 5, then y would be 10. Y is a multiple of x. Now k could be a fraction, in which case y would be less than x. This is what directly proportional means. Y equals kx. So do not forget that as we go through and convert these expressions. Next, we have inversely proportional. Inversely proportional is the same as directly proportional, except k is on the numerator and x is on the bottom. This is easy to remember because of the word inverse. It basically means you invert x and put it on the bottom of the fraction. For example, in this case, let's say k was 10 and x was 2, then y would be equal to 5. So inverse means put x under the fraction bar and keep k on top. The third type of proportion is called exponentially proportional. We won't be studying that one as much, but basically what that means is you still have k, so notice all three of these have a k factor, but in this case, inversely proportional means y is equal to k times e to the x. Completely different type of proportion, and again, we're not going to get into that one as much. Let's use a different color there. All right, now let's move on. In the future, if you take Calculus 2, you will study what's called altered exponential growth and decay. Now, exponential growth is the differential equation dy dt equals ky. With altered exponential growth and decay, the y is subtracted by b. The way to read this equation is the rate of change of the quantity y, so this part right here, is directly proportional to, so you have k times being your multiplication factor, it's directly proportional to the difference y minus b. So the difference y minus b is right here. Directly proportional means you put a k in front of it. So we're going to be taking these types of sentences and converting them to differential equations, meaning it contains a derivative, which is usually something like dy dx or dy dt, and an equation sign. If we use separation of variables, we do end up with this initial equation for y, but for this particular example, we're just focused on taking these words or sentences and converting them to differential equations. So again, the rate of change of the quantity y, so dy dt or dy dx, is directly proportional to the difference y minus b. So whenever you have directly proportional, it's always k times whatever's left. So in this case, the difference of y minus b is what comes after that. Let's get to some examples. A car travels at a constant rate of 40 kilometers per hour. So you might be thinking, well, how do I know this is a differential equation? Well, the key word here is rate. Again, every time you have a rate, you have a differential equation. So let's go through the steps to converting this to a differential equation. Step 1 is convert words to algebraic expressions, which is why I spaced this out. So the rate in which the car travels is the first part I'm going to convert. Okay? A car travels at a rate. I'm going to take that and I'm going to say dv dt. Okay? That's it. Why? Because that gives me the velocity of the car. You could write v prime, but because it's a differential equation, you typically write the rate as a fraction. So that's the first part. It's easy. dv dt represents the velocity of the car. Okay, the second part, the rate of 40 kilometers per hour. So this is going to be equal to 40. And you don't even have to put the units. Okay, in fact, I'm kind of putting too much together. We'll just write the 40 for now. Okay, so when you put that together, guess what you get? You get an equation. So for step 2, put the expressions together to form the differential equation. I'm just going to have dv dt, the velocity of the car, is equal to 40. It's very simple. Now it's a constant rate, and so that's why my differential equation is constant. In the next examples, we're going to look at ones that aren't constant. Notice that if you were to integrate this, you wouldn't even really have to do much. You just take the antiderivative of both sides, and you get v is equal to, you get position equation is equal to 40t. But for this particular lesson, we're just converting these words to variables. So that's it for the first example. Second example, the instantaneous change in pressure is directly proportional to temperature. So again, for my first step, I'm going to convert my words to algebraic expressions. So let's talk about the first part, instantaneous change in pressure. I'm going to write that as dP over dt, because as we've said many times in this class, instantaneous rate of change is just the derivative, which we can write as a differential ratio. Okay, next part is directly proportional to temperature. This is why we just went over these proportion expressions. We said directly proportional means k, some constant k times your independent variable. So I'm going to take this directly proportional to temperature, and I'm going to write k times t. Putting that together, we now have, and let's move this up a little bit so I can write this. We have dP dt, the rate in which the pressure changes, is equal to some constant k times t. And that's it. We've taken our original sentence and we've converted it to a differential equation. dP dt is equal to k times t. Very simple. On to the last example, which is a little bit more thorough. Let's read this together. It says the rate in which the population of a certain species of snake changes. So before I go any further, I'm just going to go ahead and start converting these to rates and whatnot. So let's use purple for that. The rate in which the population of a certain species of snake changes. So for population, I'm going to use P, and we don't really have to use S for snake. So I'm just going to write dP dt again. So in this case, it's not pressure we're talking about. We're talking about population, but I'm just going to write dP dt. Okay, on to the next thing. With respect to time, so you write it as over dt, is inversely proportional. So with inversely proportional, as soon as you see that, what you want to do is you want to put the k on top of the fraction. And this is going to be very small, but I'll give you more room when we write the answer. You want to go, when you say inversely proportional, put k on top of the fraction bar, and whatever comes after that is what you put on the bottom. And that's because, again, inversely proportional means k goes on the top and then your variable goes on the bottom. So that's why right off the bat, when I see inversely proportional, put k on top and then a fraction bar. So it's inversely proportional to the difference between the population of the snake and the number of top predators of the snake. So if it's inversely proportional to the difference between P and T, on the bottom of this fraction bar, you can just put P minus T. Okay, and that's actually all you have to do for this expression. That's a long sentence that was converted to K over P minus T. Question is, what differential equation would model this phenomenon? Well, this is our first part, dP dt. And as I tell all my students, the word is just means equals. So that is becomes equals, and that will put these two expressions together. And for my final example, I am going to just do that and just put them together. So for my final answer, I have dP dt, the rate in which the population is changing, is inversely proportional to, so I'm going to put my k on top, the difference between the population of the snake and the number of top predators of the snake. So that's going to be population of the snake and number of top predators. So, and this is my differential equation, folks. That's it for this lesson of converting sentences or words to differential equations. It's quite simple once you know the basics and the fundamentals and how to convert these words to expressions and equations. If you have any other questions about this lesson, let me know.